All right, the broadcast has started. Welcome, everybody, to your weekly webinar 2 with me, your mentor, Michael Floyd. I am your mentor as well as your mentee because as much as you learn from me, I surely learn and expect to learn even more from you. Now, a couple of things, some things that I've said in the previous week one webinar that I will repeat again is one thing, let's set the pace for this course. I know many of you are behind. Falling behind early is not a good idea. We need to make sure that we are ahead when it comes to being early. Things get in the way, and things will get in the way in the future as well. Family, job, let's try to stay focused and consistent. Like I've told a couple of students, knocking out 30 minutes in the morning, right? Instead of maybe cooking yourself breakfast, eat a Velveeta bar or a quick bite to eat and knock out 30 minutes in the morning, 30 minutes at night. That is 1 hour a day for each day, and you will be more than ahead and definitely have enough time to finish this program. All right. Also, every time you spend time in the program, I'd like you to write in Slack. I don't see enough feedback in Slack. I know many of you have questions, and rather than putting it in the Slack form where you have your teammates as well that can answer the question, you ask me directly if you have a question. I don't want you to ask me directly. I want you to ask it in a team environment. That way, if a teammate needs the same question and the same help or can even help you out, he will be able to help you out as opposed to only waiting for me to get back with the question. So from now on, if this question is not specifically pertaining to you and it's about the program, let's try to keep the questions asked in the groups, whether that's the 5-way group you are in or whether that's the data science channel that was provided to us. Just as long as you have a question and the question is pertaining to this Nano Degree program, let's try to ask it in the group. Okay? So our webinar for week 2 is on model evaluation, metrics, and tuning. The last few lessons that are provided in the part 1 before the project. I know we have not gotten to those lessons yet. So what I will do is I will explain very quickly exactly what those lessons will say. And also I'll provide some extra things that the lessons do not. Like I said, the lessons are pretty straightforward. You should be understanding the lessons, but I want to make sure you are prepared for a career as far as a data scientist. So not everything is taught in the program, and a couple of articles and textbook lessons that I have that I can use to help you further gain your skills. I will use those and show you exactly how to do different and better model evaluations and tuning parameters if possible. Okay, so let's jump right into it. I will share my screen. Okay, we are on training and tuning right now. The first thing I want to cover is the evaluation metrics. So evaluation metrics, pretty much you have a model, usually multiple models, and you have to evaluate how did this model perform. So one thing that the lessons start off is telling you that, hey, you need to split your data into training data and testing data. So if you have a data set and the data set, let's say, overfits or, fits very, very snug your data, and your model cannot transition to other data that will be incoming that you need to predict, then you have a problem. That problem is mitigated by making sure you take precautionary measures to not overfit your data. The same way you can go with underfitting your data. If you just have some roundabout, barely trained model and you try to test or use predictions based on data not seen, and the model is so generalized that it will not make accurate predictions or an accurate regression analysis, then you have a problem as well, and you need to fit the model more closer to the data. So the first thing is understanding the importance of the training and testing data. You split the data into a training set and testing set. You fit the data on the training set. You test it on a completely different set that you never trained the model on. And for the classification measures, for example, for a model that detects whether there is spam or not spam, there are different metrics to use in order to see if your model is accurate. So one metric is accuracy. Okay, and accuracy is pretty straightforward. So if you have the actual count of the spam and the not spam, and you predicted which one is spam and not spam, then the accuracy is just the ones that you predicted to be correct. So the ones that are spam and you predicted to be spam, the ones that are not spam and you predicted to not to be spam, those are your correct values, and you divide that by all of the data that you use to train your model on. So the accuracy is a very good metric, but in many cases you have imbalances in your data. So for example, if you have a very uncommon disease and maybe it only affects 1% of the population, then because only 1% will be in this actual positive, and you will have so many negatives as far as the people that are not afflicted by this, then to be able to tell with the accuracy, it will be very, very difficult, because the amount of negatives that you would have in a general model, of course, would be tremendously large, because hey, you have only 1% of the population that even has the disease in the first place. So sometimes the accuracy metric is not enough. And there are other metrics: precision, recall, sensitivity, specificity, that are very, very helpful as well. Precision focuses on the predicted positive values. So the values that you predicted to be positive, looking at how accurate those are. So everything you predicted to be positive. All right, so how many positives do you have given what you predicted for how many correct positives do you have, and how many false positives, which are the values that you predicted to be positive but not. For this case, we have spam and not spam. So you predicted to be spam, and it is not spam. And what we have for recall is recall focuses on the actual positive values in your data set. So recall is for the actual positives, only focusing on this column right here. Remember, precision was focusing on the first row, which is the only predicted positive. Recall is focusing on the actual positives and seeing based on the amount that you predicted to be positive that are positive, and the ones that are actually positive and are false negatives. Then you have a metric. You just divide all the actual cases by the true positives. And as you can see, for something like the 1% of the population that has this disease, similar to what I was saying before, if you're only looking at this 1% and you're seeing exactly how many of the 1% were based as positive. This is a much better metric for that, seeing if the 1% of the population actually has the test predicted to be positive when it is positive. And as you can see for precision, maybe not so much because you have 99% over here. So even if 90% of the true negatives are 90% of the actual negatives are true negatives, you still see you have 10%, which would definitely throw off your true false positives. So your precision might not be a great metric for when you have a very, very small population that you are that is sick, or that you are testing to see you are testing to see whether this is a good predictor of if you can tell who is sick based on the 1% of the population having disease. But in this case, for spam, this is a great scenario because spam, you are not really that worried about the false positive, which means that all of the spam that you predicted to be spam, and you have the you predicted to be spam as far as the true positives and the false positives, which are the ones that are actually not spam that you have sent to spam. So this is very, very important for this case because you definitely want the precision to be as high as possible because if your mother sends you an email, you want to make sure that email, which is actually not spam, does not get predicted to be spam. So this is a very important metric for a case like this where you have spam and not spam. And recall will be a very important case for when you have a small population that has a disease and you are seeing whether the test of finding the disease is accurate. And sometimes you have cases that are in between. Of course, you have cases that are in between, and based on the disease or the spam, it'll be in between as well. Whether that's a business account or a personal account as far as emails. And your F beta score actually deals with that. So it is a way to combine precision and recall. And the smaller beta is, the smaller beta is, which is closer to zero, the more precision would have an effect on the F beta score. And the larger beta is, more of the effect would be on the recall. And of course, when beta is 1, it's harmonic between precision and recall. And this is the rate of change curves. And what's important about the rate of change curves is when you are fitting your model, and based on your model training, you can tell if the model is a good fit by looking at the area on the curve and also the way the rate of change curve is, with the way it looks, of course. So the area on the curve is large, and this is a perfect model, right? So you can easily fit a linear line and separate all the data. And as you can see from this, you have an area of 1, right? So this is a perfect model in this case. In this case, you can find a pretty good split. So you still have a pretty high area, and here you have a random split because, as you can see, there's no discernible pattern to fit a model on. And for regression measures, measuring how well the regression does, you have the mean absolute error, which is just the error from what you predicted to the actual value, subtract and take the absolute value of it, and you have the mean squared error, which is the difference squared between the predicted and the actual values, and the R squared score, which is the coefficient of determination, which has to do with the sum of squares and how well a parameter can fit or can better fit your model. We will discuss more about R squared as we move ahead, because there is a lot of things about R squared that are pretty important. As far as the mean absolute error, it can work, but it's not really well used as far as a metric to interpret whether the regression is a great fit. The mean squared error, however, is a really good tool, and the R squared score is a really good tool. And with the mean squared error, you can use the mean squared error of your regression and your your sum of squares for your regression and your sum of squares for your error. And those are your mean squared error and mean squared for regression. Using those, you can get the F score, and that will tell you even more whether the additional parameter, that is the B1 or the slope in a simple case, whether that is important or whether that is significant in your model. More about that will come later. So for a bad model, this is just more R squared score. You have 1 minus, which would be 1. So what you don't want to see is you don't want to see your model barely fit the data. So if you had data all over the place, the only thing you can do is just draw a straight line similar to that. Like this is drawing a straight line. So this is a straight line and this is a straight line. And you can tell, for one, the slope in this is not significant, which is something of importance when you talk about interpreting whether the model is overfitting or not. As far as regression is, whether the slope and the other parameters, when you get to multiple variables, whether they are a good fit or whether you should remove them from your model, or that will be done soon as well. And all right, so to begin talking a little bit more about the R squared and the F score, I refer back to a data analysis class I took about 1 semester ago, and just start off right here. This is about beta 1. The nanodegree course already shows you how to derive your estimate for your beta 1, which beta 1 in this case is the slope. So this is the slope of the line for the regression, and this is the expected value of the slope. Of course, is the actual value. This is the variance, and those parameters, the beta 1 and the variance will be shown how it can be estimated, which the variance is estimated by using the mean squared error. So using the mean squared error means you have to remove 1 more degree of freedom. So you have n minus 2, which is n is the number of observations, the n minus 2 degrees of freedom. And the sum of the squares and the actual variance follows a chi-squared distribution of n minus 2. And, knowing that and given, we use this as the estimate for the actual variance, we can then say that the beta 1 minus whatever is the expected value of beta 1 will have a t-distribution based on the sum of squared error and the actual variance having a chi-squared distribution. The degrees of freedom are n minus 2. This is important because this allows us to find a confidence interval. It also gives us a t-statistic. So, you know hypothesis. So for a regression model, of course, you want to see if your slope is significant, whether you have with 95% confidence, whatever percent confidence you are looking for, whether your slope is necessary for your model. So usually this is beta 1 equals 0 because B test is usually 0. Like I said, this is usually B1 is 0. See whether your slope is actually needed in the model. If it's not, of course, you remove it from the model. This is the beta naught. It's just about beta naught. So this is, this was done in the Udacity coursework. A little different syntax, but finding the estimates for the intercept. Beta naught is the intercept. In this case, of course, your expected value is the actual value of beta naught, and this is your variance. And the variance is approximated similar to using the mean square, similar to how the variance is approximated for the intercept. And using that variance, and because it's approximated, you lose another degree of freedom, and it also follows a t distribution. And usually you do not check whether the intercept is whether the intercept is 0, because it really doesn't matter. Usually you're more concerned about whether there is a linear relationship between two values. So this is, you can test it right here. You can also get a confidence interval for beta naught. And this is just an example software. So in these lessons, R is used, but as far as any table in here, ANOVA, the F statistics, everything that are described and used in this chapters or these documents that I'm using, this can be done in Python as well. And you don't have to program the formulas. All the formulas, everything are in there. All you have to do is pretty much just search for it. These are pretty simple things to find as far as the confidence interval, the t-statistic for the intercept, the p-values. And so this is a table. Table would be similar to what you would want to see to have the estimate for intercept, the standard deviation, which is of course you're not really more interested in just manually looking up the t-statistic yourself. So using the p-value, of course, is always the easiest thing to do. So you have the p-value, you can determine just based on the p-value whether that is above or within your confidence interval limit. This is an example. What you see here is you see your intercept is 0.0259, which if it's at 95%, then the intercept is the intercept is still in with 95%. And with the slope, you have a really, really small number. So you can tell there's definitely a linear relationship because, the intercept, of course, like I said, is not really that important. but it does help make the model, so it is necessary, but the slope, determining whether there is an actual linear relationship, which based on this, being significantly small, there's definitely a linear relationship. So you're rejecting no hypothesis that there is no linear relationship between the whatever the Tocco data is in this case. And just some departure. So of course you're believing that X, these samples that you've taken from your X values are taken normally distributed, because X is normally distributed, then Y is not. Y is also normally, well, you'd assume Y is also going to be distributed. What you are what are you trying to find? You're trying to find a relationship which you will believe that both X and Y are both sampled, come from a normal population. And it's just estimating YH. So, like I said before, you have those standard errors. So, with those standard errors, you can find exactly the estimate of the variance or standard deviation in this case when you are using it to find out what, how confident you are in your guess on an estimate of Y based on a X that you have trained with. So this is, the confidence using this as a standard error based on the X that you were training with, or one of the X that you were training with, exactly what the intervals for the error you believe to be. And a different formula when you are predicting a new observation, because with a new observation, this is not something you have seen. So the interval for predicting, as far as whether it's 95% or whatever the percentage is for interval is going to be larger for predicting, because predicting, you still take into account the error term. The error term plays a significant role, because now, besides what you have here as far as finding the variance of this, the same thing, you also must take into account the variance of this error term. And that adds a 1. And you have a similar equation, but what you have here is you have 1 added to what was seen before for the 95% confidence interval for a point that you have in your model currently. And here is a chart of what I was referring to. So as far as your confidence limits, this is 95% confidence limit of what your model has trained on, and based on that, these are 95% intervals of where you believe data points will fall if you were choosing to predict something, the limits of where you believe a data point will fall if you had to make a prediction. And analysis of variance or ANOVA. Like I said before, the fact that the variance follows the chi-square distribution will be helpful, because they provide two chi-square distributions, which are before divided by the degrees of freedom. Then you have a F statistic, and this F statistic is important and can determine the same exact thing, which is whether adding a parameter or multiple parameters within your model as far as intercepts and multiple parameters, whether it is significant or whether it is necessary. So this is the F distribution, and talking about the sum of total squares, which this is important right here. The sum of total squares is equal to the regression and error sum of squares. So that is important to know. And this is the degrees of freedom, along with the sum of total squares and degrees of freedom for the regression. In this case, we only have one variable, which is the beta 1. So in order to, of course, fit the equation, you have n minus 1 equals 1 plus, this must be n minus 2 for the degrees of freedom for the error term, which of course is the case as we have seen before when calculating the mean squared error as well. And this is what an ANOVA table would give you. The mean squared errors is the sum of squares divided by the degrees of freedom, which in regression case is just 1, and the error case it is n minus 2. And this is important because the mean squared errors will give you the F statistic when dividing, and the F statistic is the mean square errors. So this is the guess for the variance, and you divide it by the degrees of freedom. So you have this is a chi-square distribution divided by its degrees of freedom. This is the chi-square distribution divided by the degree of freedom. And so what you have is an F distribution, and this F distribution is another test for whether a parameter you're adding into your model is significant or not. The same as using the p-value from the t-test. So as you can see, we have I believe the same number, which is 4.45 10 to the negative 10. So the same exact number. This F-test is just the square root of the t-test. So it's the same exact test in this case, but in more cases, the F-test is important because you might be adding multiple variables into the equation at once. That will be important later on when I explain that. Coefficient determination, the sum of the squares for the regression minus or divided by the total squares, which is 1 minus the sum squared error divided by sum of total squares, which is exactly what we saw in our model, right? This is the total squares for this. And this is the squares. This is based on the error that is occurring. This is the square from that. So exactly what we saw from the R squared from the Udacity tutorial. And properties of R squared, of course, between 0 and 1. That's why they call it R squared. That's the goodness of fit. One measure of how it literally fits the data. More information on that right here. And because it is 6:35, I will leave this go to multiple regressions. For multiple regression, so you have multiple parameters you are looking to see whether you want to keep in the model or add into the model. And the sum of squares functions in a similar way for multiple regression as it does for regression. So one thing is the sum of squares for the regression for all the parameters that you are adding is equal to the sum of squares error that was previously there minus the error that you have picked up with, minus the error you have taken from, minus the error you cannot define from your model. So this is the error that was not defined by the model without these parameters, and this is the error defined by the model with all these parameters. And so subtracting these two will give you the error that we can actually determine to be a product of adding all of these parameters, j plus 1 through x of k. And it's just an example of what I was saying. So you're adding x2, x3, and you previously only had x1, x4, x5. So the error that you could not explain from x1, x4, x5, subtracted by the error now that you could not explain by 1, 2, 3, 4, and 5 is what the 2 and 3 have accomplished by being added to the model. And of course, because the SS, it's because the total squares is the regression minus is the regression plus the error. You can also write it like this. So yes, because the total squares is not dependent on how many predictors you have in the model. And this is just a decomposition of a NOVA table, and just showing you. Okay, so you start off with just one, you add another one. Given that you have this one, then you add another one. Given that you have these two in the model, so you want to be able to see how much is being explained by adding these into the model. And because with each addition, you do lose a degree of freedom as well. So here's an example, a really good example. So you have body fat, and what you have here is you have your tricep, thigh, mid-arm, using the measurements on your tricep, thigh, and mid-arm to determine your body fat. So start off first, whatever goes into the model first is used first. You have your tricep, then thigh, then mid-arm. So you're adding your tricep, just your tricep itself produces 352 as far as how much error is obtained from just adding the tricep, and that's significant. And from the FI, you can tell that it's significant. And then you add the thigh, and that's 0.033. It's less than 0.05 based on what you have in the model. And then you add on the mid-arm, and as you can tell, the mid-arm is not significant based on just adding the tricep and the thigh. So, like I said, the results can be used X2 through the SSR, given X2 and X3. The amount of error you are able to determine from your model from adding X2 and X3, given you already have X1, is the amount of error that you have taken from, explained from with S2, which is this, plus the amount of error that you displayed from S3, which is this as well. So, but as we can see, using a different model, which is pretty interesting. If you use just the thigh, well, if you use it in a different order. So here we had tricep, thigh, mid-arm. We have thigh, tricep, mid-arm, and this one. We switch the order, and what we can see is that more of these squares is better determined by just the thigh than the tricep. So using just the thigh, you even get a lower and more significant p-value. They're both pretty significant, but when using the thigh, you can see that the tricep and mid-arm become obsolete as far as the p-value and what they should do in the model. And they shouldn't be in the model, obviously, because they do not, given the addition to it, they did not explain enough of the error in the model. And 641. This is just showing the mean squared error. And of course, you can always whether adding the parameter is important. And if it's not, this is the F statistics. So of course, you want a very low p-value to say, hey, it's important that we add this. We reject the null hypothesis. And the body fat example for mid-arm is what they're using. 0.188. It's the same thing because it's the last thing added, so it's the same thing. So you have 0.188 as far as the F statistic, right here. 1.88 as far as the F statistic. And you can also test whether several of them equal 0 at the same time, because like I said, you can band two together, so whether x2 and x3 given x1 are important, by adding one at a time and decalculating the mean squared of the regression. And so this is the F statistic for that. So what you've done, all you do is just add up the sum of squares. So for the when both thigh circumference and mid-arm circumference can be dropped. So for when you want to know whether thigh and mid-arm can be dropped, so it's the last two in the model. So it's this one that they're talking about. What you do is you add up the sum of squares because you have two variables. You have 2 degrees of freedom. So these total that is understood by the regression divided by the degrees of freedom, which is 2. And that gives you the mean squared error. And then you portion the mean squared error for the entire model divided by 16. And that is the F statistic you have, which was not significant. But it's right here. Whoops. It's right here. Okay, yeah, so 3.63. It's just more on how you can use the F test to test whether different parameters equal 0. Pretty much similar things. I'm going to dive more into that. You have multiple, you're adding multiple things in at the same time, and it's the F statistic. And the R squared, given you're adding a perimeter model, the R squared tells you exactly how much is explained by adding to just another thing you can use instead of the F statistic as well. And for the body fat example, we call it partial determination because had the coefficient of determination because you're given one and given the variables that you have. So what percent? So you have the error that is not explained, and you have the error that is explained by adding in a variable, what error is captured by adding in that variable, what percentage. And that's what the R squared score shows you. And you have multi-collinearity. So, getting the actual estimates for this model, we can see that well, here are the estimates, but when we look over here, we see that none of the p-values for these estimates are significant. But this is the same thing we've did before. We know that based on what we've seen for the f-test, that there is definite relationship between tricep and thigh, and especially thigh. And looking at the adjusted R score of 0.76 is a pretty good R score to have, and the F statistic is very, very high. You have a p-value which is very, very low as well. So you can tell this model must be significant in some respect. But what's going on right here? What you have is you have correlation between two of the variables within which you are trying to model, which you're using. So when you and these are multiple models they are using. So you have fat and only triceps, and you see that this is significant. You have a p-value that is significant. You have fat and thigh, which have a p-value that's significant. You have tricep and thigh, which is one is almost somewhat significant, and you have tricep thigh, mid arm, which none of them are significant. And looking at plotting them together, you can see there's definitely a relationship between thigh and tricep, which is the problem in the model. So the way to deal with that is either remove one from the model, use a principal component analysis. Those are two different ways you can use in order to remove that collinearity. And running out of time a little bit, but for training and tuning. Training and tuning. So before, what they discussed was using only a training data set and a testing data set. But what you will find is that when you're training now, you want to know when exactly you want to stop training. And having another subset of the data set in order to determine exactly when that goes off, that is a great thing to have, and that is what's called a validation set. So using the validation set, that is usually how, well, that is always how I use it. You have a training, testing, and validation data set, and I train the model and using the validation data set and decide when to stop training. And this is just an example of the learning curves to detect when it's over or underfitting. And what you want to see is you want to see you want to see a convergence between. Let me click on this. You want to see a convergence between what you are validating and what you are training, and of course you want this to be as high as possible. So basing your learning curve, we see right here for the just regression, I train data set with training. We end up with a score of a little less than 0.7 for our training and validation. We have a little less than 0.4. And of course, obviously, the decision tree is better than the decision tree. You have, we really more focus on validation. For validation is a lot higher for the decision tree and support vector. It doesn't look as training at all. So, that's that in that case. And grid search. Grid search allows you to look at how your model will behave, giving you change different parameters within your model description. So for example, for decision trees, you can change exactly how many are required to be in a node in order to split, how many are required to be in a node just to be a node in general. You can determine how many splits, maximum amount of splits. There are many things you can use within the decision tree. And yes, so just many parameters you can use. And researching through parameters most of the time provide you with the best model. I use that extensively as well as the K-fold cross validation. So with that, I will stop the talk. We have 9 minutes left. And if there are any questions, let me know if there are any questions. And I will be sure to answer the questions. I do not see any questions on here. So what I would like you to do is, well, first, if you can, post questions on here. If you can not, then or if I can't see them, I'll post them in Slack as well. Looking through both channels, and hopefully I see something from either Slack or I see something from the YouTube. I see something from G. Yes, I'll give you 1 second. Hold on. All right, I had to blow my nose for a second. Excuse me on that. No, I do not see any postings or any questions on the chat or in Slack. So what I will do is I will end it here. And like I said before, for just the closing notes, if you have a question, you don't have to directly message me. Everybody sends direct message. What I want you to do is I want you to post a question in your group or in the channel that was provided to us. And I just realized I was not on the headphones. So like I said before, because I don't see any questions on here, I'm going to cut this short. I was leaving the last 2 minutes to answer questions, but like I was saying before I put the headphones in, final closing notes. Everybody asks me questions personally, and that's why I created the groups. I like the group to get involved. I like you to notify the group of your progress, how far you've gotten, 30 minutes today, 1 hour today. How far are you? Just say, hey, I'm struggling with this. Whatever you need the help for the group to do, let me know. Let the group know. And, keep it posted in the group discussions. And also, like I said before previously, you must have something you would think about doing if you do not land a job as a data scientist, analyst, or anything within this. So, write blogs, YouTube videos, maybe create a Udemy course, be Udacity mentor, and something that's maybe not even part of data science, right? You might degree in food, whatever you can do. Just make sure that you have something that you are also focusing on as well along with this. I'd be interested in hearing what you think, what your plans are. But of course, the same focus is to make sure we all get through this. Which you all get through this of 30 minutes in the morning, 30 minutes at night, 7 hours a week. For the next week, all you do is just finish the last couple of lessons. I believe the last lessons are the ensemble, model evaluation, and training and tuning, which are maybe 3 hours long. It should be easy to complete. Once you complete that, hopefully you start on the project. If not, next week we will all start on the project. So I'm excited to begin the project, working with the project. We're on the first project almost, it seems. I'm looking forward to the progress. Make sure you tell your team leaders exactly what you are doing and how you progress as far as this week ahead. And I will remain in touch. All right. Thank you.